Energy is the ability to do work. There are two main types of energy, kinetic and potential. Some types of kinetic energy are thermal, sound, light, and electricity. Some types of potential energy are elastic, chemical, gravity, electricity, magnetic, and nuclear.
The equation for kinetic energy is 1/2 mv squared, where m is the mass and v is the velocity. The equation for gravitational potential energy is mgh, where g is the acceleration due to gravity and h is the height. The equation for potential energy of a spring is 1/2 kx squared, where k is the spring constant and x is the displacement. The law of conservation of energy states that the total initial energy has to equal the total final energy.
So for our first problem, we are going to have a ball with a mass of 5 kilograms resting on top of a cliff that is 15 meters tall, and we are simply going to find the potential energy of that ball. So we are going to solve this using the guess method. So the mass of our ball is 5 kilograms. Our gravity is 9.8 meters per second squared, and the height of our cliff is 15 meters. So our unknown is the potential energy, and the equation we will be using is UG equals mgh. And we don't have to change up this equation at all. So we just need to plug in our numbers. So our final answer is 735 joules.
For this problem, we will have an object with a mass of 10 kilograms on a string that falls in a circle. The string's length is 4 meters, and this is the point in which we have to calculate the increase in kinetic energy as it moves from here to here. So we're going to use guess method. Our givens are already given here. 10 kilograms for the mass of the object. Our height is 4, but it's 8 because that's the radius. And then gravity. Unknown is our gravitational potential energy. So we use the equation UG equals mgh, and we don't need to change anything about the equation, so we simply plug in the numbers. Into our calculator to get the final answer, which is 784 joules. That's the kinetic potential energy, which is all converted into kinetic energy by the time it reaches the bottom. So we can actually say that Ke at the bottom point is equal to 784 joules. And that's our final answer. So for this next problem, we have a roller coaster where the car is up here and has a mass of 100 kilograms at a height of 20 meters. And there's a second hill where the height is 10 meters. We're looking for the velocity here at the top of the second hill. So our givens are the mass of the roller coaster is equal to 100 kilograms. The height of the first hill is equal to 20 meters. And the height of the second hill is equal to 10 meters. Our unknown is going to be gravitational potential energy for both cases. Our equation is going to be UG equals MGH, and we don't need to change it for this situation. So we simply plug in the numbers for both cases. The mass is 100 kilograms. Gravity is 9.8 meters per second squared. And the height is 20 meters. And for the second one, same mass, same acceleration due to gravity, and a height of 10 meters. So we plug these into our calculator to get the final answer for this part of the question, which is 19,600 joules and 9,800 joules. So now that we have two new givens, which are the potential energy of the first hill, which is 19,600 joules, and the potential energy at the top of the second hill, which is equal to 9,800 joules. And the difference between those is how we determine the velocity, and that's going to be equal to 9,800 joules. Take this minus this, and that's that. So our unknown right now is velocity, and the equation we're going to use is KE equals 1/2 mv squared, because kinetic energy, all the potential energy is going to be converted into kinetic energy. And we need to change the equation to solve for velocity. So our equation is then square root of 2ke over m is equal to velocity. And we simply plug in the numbers, 9,800 joules, 100 kilograms, and we plug that into the calculator. Sorry, this is a 2. Plug that into the calculator to find the final answer, which should be velocity is equal to 14 meters per second at the top of the second hill.